Welcome back to the Blockchain Fundamental course. So in this course, we are learning about a lot of fundamental details of how blockchain is constructed. We're going to see about Merkle Tree in this video. Merkle Tree is a very important data structure that is used in blockchain. In each block, you will have set of data or transactions, and all the data or transactions will be converted into hash, and finally we will have a Merkle root, and that Merkle root will be included in the header of the block. So let's dig into the details of Merkle tree and let us understand how Merkle tree works and how does it work for building up complex or futuristic protocols, something like ZK proofs, which are widely used in Ethereum. Merkle tree, it has taken the name from the mathematician Ralph Merkle, and this is not just a new concept. Ralph Merkle, he patented the idea of Merkle tree in the year 1979, and later this idea has been taken into the building of the blockchain technology. It's just a binary hash tree. We have learned about what is hashing in the last video, and this is a binary hash tree. In quite a few minutes, we'll be learning about what is this and how it works. Every leaf in the Merkle tree, it will have a cryptographic hash of the data, which uses hash function, and every branch also has a cryptographic hash. But whenever you take a node, internal node, it will have the cryptographic hash of both the children. And the root will contain hash of all hashes, or we can say it will have the hash value of all the transactions. So even if a small modification in the transaction will be affecting the hash root, hence it is completely immutable. Okay, what is a binary tree? Binary tree is a tree which has two children. So binary tree is a data structure basically. So what is a data structure? The data structure stores some information and it helps us to retrieve the information in a much faster way. Depending upon each type of data structure, the way in which we store the data and the way in which we retrieve the data will be different. So let us assume this tree is similar to the tree that we have in our real life, but it's just an inverter tree. The root will be in the top. So here 7 is a root, and 5, 6 are children of the root 7, and 1, 2 are children of 5, and 3, 4 are children of 6. The nodes that do not have any children or the further branches, they are called as leaf node. And the nodes that are other than the root and leaf, they are all called as internal node. So here in this case, 5 and 6 is called as an internal node and 7 is a root node. So you can say 7 is a root and 5 and 6 are internal nodes and 1, 2, 3, 4 all leaf nodes. There is a special binary tree, that is, this Merkle tree is a special binary tree. So why it is called as a special binary tree is each internal node will have the hash of its left child and its right child. So when you say you have a data, each data will be converted into its hash, and from that hash we can say this L contains a hash of left child and hash of the right child, which are in turn hashes themselves. And this one will have the hash of left child and right child. And finally, the root will also be having the hash of all transactions. Let us see how this Merkle root construction is done. Assume you have 4 transactions, 1, 2, 3, and 4. And we'll be computing the hashes of each transactions and we'll be storing that in the leaf node. So h of 1 is a hash of 1, h of 2 is a hash of 2, and so on. Now when you take the next level, from the hash value of h of 1 and h of 2, a new hash will be computed. That is hash of h of 1 and h of 2. That will be the final value of A. And what about B? The hash of left child, that is h of 3 and h of 4 will be combined together and the final hash will be taken and that will be taken as B. And now we have got A and B. Now we'll be able to construct the hash of the root. How do we construct? Again, the hash of A and hash of B together, you take hash, you will get the roots hash. So you can say C will be equivalent to hash of A and B, which are themselves their hashes. This is how Merkle root will be constructed. This hash is what you call it as root hash, and this is a hash that will be added in the header of each block. Merkle tree is used for checking the integrity. How do we check the integrity? Let us assume you have constructed a hash and finally you have arrived at a root, say C. Let us take this transaction h of 4 is being modified to become h of 5. That is, fourth transactions is modified, so the hash of that transaction will be stored here, which is h of 5, which will in turn will change this hash. So this hash will no longer be B, now it will become E. Now when this f is constructed, hash of A and hash of E will not lead to getting hash of C. It will definitely get a different hash. So when these two hashes are not same, then we can understand that all the transactions that we have received is not correct. So it is used for checking the integrity. So this integrity check can be done in order to ensure that the transactions themselves are not even changed, or even not even a single change has been done to the transactions. That is very important use case which is used in the verification. When I wanted to claim that a particular transaction is part of a block, then I don't want to give the entire block's data. It is enough to share only certain details from the entire Merkle tree. Let us see what are the details that we wanted to share. Now, I'm going to prove that transaction 4 is part of the Merkle tree. So what I need is hash of 3. So we don't want even the other details or the details of the other transactions. We just need only the hash. So if we have hash of 3 and if we have hash of A, only with these 3 details we'll be able to compute C. Let us see how it has been done. So from 4, directly you can calculate the hash, so you get hash of 4. And we have got hash of 3. You substitute it here. You take hash of 3 and hash of 4, you get B. Now, since we already have the hash of A, these two hashes can be combined together and the final hash value can be taken. If the resultant hash is C, then we can prove that transaction 4 is part of this Merkle tree. So we haven't even revealed the entire Merkle tree. We have given only the details of the transaction that we wanted to prove and only some set of other hashes. One use case is we check the integrity of a particular transaction, or we can say the entire block can be checked for the integrity using this Merkle tree. And the second use case is verification of presence of a transaction. We might think, why do we want it to hash in multiple levels? Why not we hash all the transactions together and finally we get one final hash? So if the getting final hash is the only objective, we could do that. Let us see what will happen when we hash all the transactions together to get the final hash. When it is being done, we will have list of all transactions. Approximately, we will have around 1,000 transactions or anywhere between 500 to 1,000 transactions in a blockchain block. Or we can say precisely each Bitcoin, which is a very famous application of a blockchain, will have around 500 to 1,000 transactions in a block. When we get a final one single hash of all transaction, still we have the hash value. Now, if I wanted to prove that a particular transaction is part of this transaction, then what do we need is we need all these 1000 transactions. So what I should do, this 1000 transactions should be taken into account and the hash value to be computed. And now this hash value should be checked with the existing hash value. If both are same, then we can say that a particular transaction was part of a block. But do you think really it is possible to download all the 1000 transactions in a node which is very, very light? Or we can say if you are using any mobile to access a Bitcoin network, will that be possible to download all the 1000 transactions and compute the hash? It would be complex. We understood with this picture. So we have a lot of data that are part of the entire Merkle tree, and this each data has been converted into the hash. And now the final hash will be computed from computing all the hashes, and finally we get the root. If we wanted to verify a particular transaction, just to verify a single transaction, we need all the hashes of all the rest of the transactions, and only then we'll be able to compute the root. So if this is 1000, then we need 1000 transactions, so the algorithm will become order of n. But let us consider how we check the integrity or verifying whether a particular transaction is part of the block. In Merkle tree, we need only this set of details. Now let us take, you wanted to verify this transaction. So if you wanted to verify this transaction, then you need hash of this one. So with this hash, you can calculate the hash of these two things, and you can get the hash of this data. And with this hash, you'll be able to compute this hash, and with this hash, you'll be able to compute this hash. And if you have this hash and this one, finally you can compute the root. So when you check for the same set of 16 transactions, you required only 1, 2, 3, 4, 5 data to finally compute the root. But in the earlier case, for the same 16 transactions, you need 16 data. So now using Merkle tree is very efficient. So considering the complexity of the algorithm, you have 1000 transactions and you have computed the root hash through Merkle tree. Now, if you wanted to verify whether a transaction is part of the tree, then you would be requiring only log 2 of 1000, because the binary tree has a complexity of order of log n to the base 2. So we can say log 2 of 1000, which is approximately just 10 data. And from the 10 data, you'll be able to compute the root hash, and finally you can compare. If you compute the hash from all the 1000 transactions, you will require the computation to be done, or the computation of this hash will take place for 1000 times. But now it's just only for 10 times, which is in logarithmic complexity, which is more efficient. So Merkle tree is very, very efficient in case if you wanted to verify any particular transaction. This verification is what you call it as Merkle proof. So what is Merkle proof? Using Merkle tree, you prove that the data is belonging to a particular Merkle tree. So you don't want it to store the entire data set to prove that the transaction is part of a Merkle tree. So what you have to do is, you wanted to store only log n times of the entire tree size. So if you wanted to prove whether this HK is part of the transaction, you require HL and you require HIJ. From this, you can compute this hash. So all the dashed line nodes can be computed, and all the blue colored nodes data is what we require. So we hardly require only 1, 2, 3, 4 set of hashes to finally prove that HK is part of the Merkle root or this Merkle tree. So it becomes way more easier than hashing all the transactions together. Okay, so coming to the Merkle tree properties. It is a perfect binary tree, and the number of leaf will always be 2 power n. That is, even if 1 or 2 leaves are missing, the same data will be replicated to the nearby leaf. And each node will either have 0 or 2 children. So let us assume you don't have a data here, that is, this HP is not present. So what will happen here is this HO will be copied here as well. So now this becomes a HO. It is a perfect binary tree. So every node in that binary tree will have 0 or 2 children at the most. And all the leaf nodes will be in the same level. So the Bitcoin uses Merkle tree. Every transaction in the Bitcoin will be computed with the hashes, and finally the Merkle root will be constructed as we have seen. And this Merkle root will be part of the block header. The entire block will contain the transactions and the hashes of all the transactions together, and the Merkle root alone will be part of the header. And each header will have the previous hash, which will be the hash of all the data that were part of that particular block, including the Merkle root. So now, since this Merkle root is also a hash value, even if you try to modify any transaction in this block, this will affect the Merkle root. Hence, modifying the hash of this block, and when this block's hash is modified, the previous hash will be modified. And if this is modified, then this entire block's hash will be modified, which will be affecting all the further blocks. Hence, now, because of this Merkle root and the Merkle tree, the entire blockchain will become immutable. So the immutability is preserved through this Merkle root. Okay, how Merkling is being done in Ethereum? So Merkle tree in Ethereum, it's way more complex than the Merkle tree that we have discussed right now. So in the future videos, we will be discussing about Ethereum and also all the fundamental concepts of Ethereum. And we will also learn about how to write a smart contract in an Ethereum blockchain as well.